15.3, what does the value of K mean? If the equilibrium constant is much greater than 1, the reaction is product favored because the product predominates at equilibrium. If the equilibrium constant is much less than 1, the reaction is reactant favored. That is, the reactant predominates at equilibrium. We can think about this in terms of writing the expression for the equilibrium constant as products over reactants. If we have products over reactants and that quotient is greater than 1, then we know the numerator has to be greater than the denominator. Likewise, if the quotient products over reactants is less than 1, then we know that the reactant or the denominator must be the greater value. Sample exercise 15.2, converting between K sub C and K sub P. In the synthesis of ammonia from nitrogen and hydrogen, or better known as the Haber process, K sub C is equal to 9.60 at 300 degrees Celsius. Calculate K sub P for this reaction at this temperature. The relationship between K sub C and K sub P is given by the equation 15.14. Kp equals Kc RT to the delta N. To apply that equation, we must determine delta N by comparing the number of moles of product with the number of moles of reactant. There are 2 moles of gaseous products. We know this from the coefficient. And 4 moles of gaseous reactants. That is 1 mole of N2 and 3 moles of H2. Therefore, delta N is equal to products minus reactants. 2 minus 4, or negative 2. Remember that the delta functions are always based on products minus reactants. The temperature is 273 plus 300 degrees Celsius, or 573 Kelvin, and the value for the ideal gas constant R is equal to 0.0821 liter atmospheres per mole Kelvin. Using the K sub C value given, 9.60, we therefore have a relationship calculated between K sub P and K sub C, and we get 4.34 times 10 to the negative third. This is our K sub P value for the reaction at this temperature. Please complete the practice exercise. Sample exercise 15.3, interpreting the magnitude of an equilibrium constant. The following diagrams represent 3 different systems at equilibrium, all in the same size containers. Without doing any calculations, rank the 3 systems in order of increasing equilibrium constant. If the volume of the container is 1 liter and each sphere represents 0.1 moles, calculate Kc for each system. Okay, so the more product that's present at equilibrium relative to the reactant, the greater the equilibrium constant. In other words, if our equilibrium constant is products divided by reactants, if our numerator is a bigger value, then our K sub C value is going to be larger as well. The equilibrium constant is given by the concentration of products over reactants. Each box contains 10 spheres. The amount of product in each varies as follows. I contains 6. The amount of product in each varies as follows. Box 1, 6, box 2, 1, and box 3, 8. Thus, the equilibrium constant varies in the order 2 is less than 1 is less than 3. In box 1, we have 0.6 moles per liter product and 0.4 moles per liter reactant, giving an equilibrium constant of 0.6 divided by 0.4, or 1.5. You will get the same result by merely dividing the number of spheres of each kind. 6 spheres of product divided by 4 spheres of reactant is equal to 1.5. In box 2, we have 0.1 mole per liter product and 0.9 mole per liter reactant, giving K sub C equal to 0.1 over 0.9, or 0.11. You get the same result by dividing product over reactant, 1 sphere divided by 9 spheres, or 0.11. In box 3, we have 0.8 mole per liter product and 0.2 mole per liter reactant, giving a K sub C value equal to 0.8 divided by 0.2, or 4. We get the same result by dividing 8 spheres by 2 spheres. Again, product divided by reactant. These calculations verify the order from A. Imagine that there was a drawing like those above that represents a reaction with a very small or very large value of K sub C. For example, what would the drawing look like if K sub C is equal to 1 times 10 to the negative fifth? In that case, there would need to be 100,000 reactant molecules for only one product molecule. But then, that would be impractical to draw. Please try the practice exercise. Manipulating equilibrium constants. The equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. So here we have N2O4, dinitrogen tetroxide, being converted to nitrogen dioxide. The equilibrium constant is products over reactants, or 0.212. The equilibrium constant for the reverse reaction, nitrogen dioxide to dinitrogen tetroxide, is simply the reciprocal of the forward reaction. The equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to a power that is equal to that number. In the case of this bottom reaction, if we multiply our equation by 2, we now have product NO2, and this time it's to the 4th power, divided by N2O4 squared, and our equilibrium constant is raised to whatever multiple was used, whatever was multiplied by the expression. In this case, we multiplied by 2, so that becomes our power. The equilibrium constant for a net reaction made up of 2 or more steps that are combined using the Hess's law is the product of the equilibrium constant for the individual steps. So let's do some examples of these. Sample exercise 15.4, evaluating an equilibrium constant when an equation is reversed. The equilibrium constant for the reaction of N2 with O2 to form NO is equal to 1 times 10 to the negative 30th at room temperature 25 degrees Celsius. Using this information, write the equilibrium constant expression and calculate the equilibrium constant for the following reaction. So we can see that the reaction has just been reversed. And so the equilibrium constant expression is a quotient of products over reactants, each raised to a power equal to its coefficient in the balanced equation. The value of the equilibrium constant is the reciprocal of that for the reverse reaction. So for our forward reaction, the expression is, for equilibrium, would be NO squared over N2 times O2. And this would be the equilibrium constant. For the reciprocal, we have to flip the reaction around. And now we have our N2 and O2 as our products. So here we have N2 times O2 over NO squared. Again, the coefficient becomes the exponent. This reversed reaction is equal to the reciprocal of the forward reaction's equilibrium constant. So we're going to take the equilibrium constant, 1 times 10 to the negative 30th, and find its reciprocal, which is 1 times 10 to the 30th. Practice exercise. For the formation of ammonia from nitrogen and hydrogen, K sub P is equal to 4.34 times 10 to the negative 3rd at 300 degrees Celsius. What is the equilibrium constant for the reverse reaction? So again, the rule is, if you're trying to find the equilibrium constant for the reverse reaction, you take the reciprocal of the forward reaction. So all we would need to do to get this answer is divide 1 over 4.34 times 10 to the negative 3rd. Okay, this time we're going to use another rule. We're going to combine equilibrium expressions. We're given 2 equations with their equilibrium constants, and we're asked to determine the value of the equilibrium constant for the sum of these 2 reactions. Now we can see that we cannot simply add the first 2 equations to get the third. Instead, we need to determine how to manipulate the equations to come up with the steps that will add up to give us the desired equation. So if we multiply the first equation by 2 and make the corresponding change to its equilibrium constant, that is, raising it to the power 2, this is the expression that we get. We're doing this because we can see in the overall expression that we have 2HF. That indicates to us that this reaction had been multiplied by 2. So we're going to take the equilibrium constant, 6.8 times 10 to the negative fourth, and raise it to the power 2 since we multiplied the reaction by 2. Reversing the second equation and again making the corresponding change to its equilibrium constant, that is taking the reciprocal, would give us this expression. So why are we doing that? Why are we reversing the second? Okay, so in the total equation here, we have the H2C2O4, or the, I think that's oxalic acid, on the product end. And here it's on the reactant end. So I know that this reaction has to be reversed. And when we do that, we have to take the reciprocal of the equilibrium constant. So that's being done here, 1 over 3.8 times 10 to the negative sixth. Now, once I have my new equilibrium constants, again, in this one we multiplied by 2, so we took the equilibrium constant and raised it to a power of 2. In this one, we flipped the equation around, and so therefore we took the reciprocal of the equilibrium constant. When we add these two together and get that total expression, we have to multiply, not add, multiply the two equilibrium constants together to get the desired equilibrium constant. Please try the practice exercise.